In this lesson, we're going to review our knowledge of the end behavior of rational functions. But first, let's make sure that everyone knows what a rational function is. In the word rational, we should always see the root word ratio, and ratio should make us think of a fraction. So a rational function is simply a function that is a fraction with algebra both on top and bottom. In particular, though, we're going to be looking at the rational functions where we have a polynomial both in the numerator and the denominator, and our favorite names for these polynomials are p of x over q of x. Now when we consider these, there are three very distinct cases when we have a polynomial p of x over q of x. In our first case that we're going to consider, the degree of the numerator is greater than the degree of the denominator. Remember, the degree lets us know which grows much faster. And so as x goes to infinity, if the numerator has the greater degree, then the numerator is going to grow to be a much larger number over the denominator, which is going to be relatively smaller. And the closer we get to infinity, the more that discrepancy is such that this is going to approach either positive or negative infinity. The way we will know whether it's positive or negative is by the sign that is determined by the leading coefficients. So determined by the leading coefficients. And I've got this abbreviation, and up here it's sitting here so you know what I'm talking about. All right, our next case is the opposite. The degree of the numerator is less than the degree of the denominator, which means that as x goes to infinity, my number on top is significantly smaller than my number on bottom. And we know from having studied this before, if we divide by larger and larger and larger numbers, we end up at closer and closer to 0. And it doesn't matter whether you're heading to positive or infinity or negative infinity. With polynomials, this will be the case for both directions. Our last case is where the degree of the numerator equals the degree of the denominator. In this case, both polynomials are growing very similarly, and the only difference is going to be the leading coefficients as to how fast they're growing in comparison to one another. So as we're approaching infinity, the only terms that really matter are the leading terms, and we're going to take the leading coefficient of p of x, which is our numerator, and divide it by the leading coefficient of q of x, and that number will be where our y value is going to head to. All right, I know all of this is review, so I want to give you the chance to see if you remember how to do all of these. And you can try all three of these before I give an explanation. So I encourage you to pause the video now and then come back and I'll give an explanation. All right, welcome back. In this first one, hopefully you noticed that the degree was the same on the top and bottom. So they both have a 2. So we just had to take the ratio of our leading terms. And so 3 divided by 1, and this would go to 3, both as we're approaching infinity and negative infinity. And let's take a look at the graph so we understand how that looks. Here is the graph of this function. And we can see that, yes, there is this horizontal asymptote that is at 3, and as x goes to infinity, f of x is heading to 3, and the same thing as x goes to negative infinity, f of x is heading to 3. Let's look at our next example. In the next example, when we were comparing the degrees of the numerator and the denominator, we should have noticed that the denominator had the larger degree. That means the denominator gets much bigger, much faster, and when we divide, we're dividing by a very large number, which means both of these will be 0. Let's take a look at the graph. Here's the graph, and we can see that both as x approaches infinity here, f of x heads to 0, and same thing here. Now in this graph it looks like it's actually touching the x-axis, but we could zoom out and see that there really is always space between the x-axis and this. It is approaching 0. It doesn't actually equal 0. All right, in our last example, we should have noticed that the larger degree is actually on top now. So that means that the top is going to be growing faster. And so the question is it heading to positive infinity or negative infinity? And when we're doing this, we really just want to ignore all these other terms, because as we get to these really large terms, it's only the leading terms that make any difference. So as we head to positive infinity, we can see, well, a positive number cubed times 5 is going to be positive. And down here, a positive number squared times negative 5 is going to be negative. So we've got positive over negative, which means this is going to head to negative infinity. Whereas when I head to negative infinity, on top, a negative number cubed is negative times 5 is still negative. Let me actually write this over here. So on top, we've got this negative number. And on bottom, when we square the negative, it becomes positive, but positive times negative 5 is negative. And so we end up with a negative over a negative, which means we're going to be going to positive infinity. All right. So let's take a look at that graph. So when we look at the graph of this one, you might notice from pre-calc you'd say, oh, there's an oblique asymptote. And you'd be right, and you could do long division to figure out the oblique asymptote. But in this problem, that's actually not what we're concerned with. We are just concerned with the M behavior being whether it heads to a specific number or to infinity or negative infinity. So we can see this is going down, which means as x approaches infinity, f of x is actually heading negative. Not very fast, but it is heading to negative infinity. And as x approaches negative infinity, f of x is going to approach positive infinity. All right, let's move on to our next slide. And in this one, we have a slightly different situation. We still do have a polynomial on top and bottom, but they're in factored form. What do we need to do to figure this one out? And what I want you to realize is that all we've been talking about to figure out what happens is just the leading term. So in here, all we really need to know is our leading term. So when I square x minus 3, the leading term is x squared. When I take it times x, I get x cubed on top. And there'll be other terms, but it really doesn't matter what they are. Down here, in the first binomial, I'll take every term here times every term there, and then I'll take that product times every term here. But the only term I'm concerned with is the one that's going to give me my highest degree. And so when I multiply all three x's, that's that one. So my leading term here is negative 2x cubed plus dot, dot, dot. And so in this case, my as x approaches infinity, positive or negative infinity, I see that the degree is the same on top and bottom. Therefore, f of x is going to approach negative 1/2 in both cases. Now the last function we're going to consider is this one. It's a rational function, but it does not have a polynomial on top and bottom. In fact, it has e to the x. And what we want to consider is how does e to the x behave in comparison to our polynomials. So I have our spreadsheet that we had from our last video, and I'm going to add in a column where I have e to the x. In Excel, you actually type in exp, and we'll just put in the number. So this first one would be e to the first power, and there's a number we should be familiar with, 2.718281828. It does not keep repeating like that forever. But that is rounded e. And then when we fill this down, we're going to see that this number grows much, much faster than any of these, where we had up through x to the fourth. And you could try this if you take it down far enough with any power of x, e to the x grows faster. All right, so what does this mean? Over here, as x goes to infinity, f of x, because the bottom grows faster, let's see. So this grows faster. So as x approaches infinity, f of x is going to approach 0. But I need to point out that this is only the case as x approaches infinity. What happens as x goes to negative infinity? And let's just take a look at the graph, sneak a peek, and then we'll come back and explain what's going on. So what we just said makes total sense here. Here we go. We've got x heading to infinity, and f of x is heading to 0. But it doesn't head to 0 on this end. We see it going down very sharply. So it doesn't head to 0 on both ends, and that's because we're not working with a polynomial here. Let's go back to the equation and consider what happens when we put in a negative number. Just for our situation, I'm just going to even put in, say, negative 10. So let's take negative 10 to the 5th plus 10 times negative 10 squared plus 200 all over e to the negative 10. Now I'm nowhere near negative infinity, but in our graph we weren't that far, and we saw, let's take a look at that graph again. Here we are, we're only at negative 2 point something, and we have gone way down already. So let's see what happens when we do that. When we evaluate this, this whole thing down here was some negative number, so a large negative over e to the negative 10. Well, what does a negative exponent do? What we have is a large negative times, and when I bring this up, it becomes e to the 10th. So I've got a large negative times e to the 10th, which is negative. And so what happens here as x approaches negative infinity, f of x also approaches negative infinity, just like we saw in the graph.